At the eastern edge of the Himalayas, the Yarlung Tsangpo River cuts through the deepest canyon on Earth. Here, the water plunges almost 2,000 meters within just 50 kilometers, creating enormous hydroelectric potential. China plans to harness that energy through the Medog hydropower project, a proposed 60-gigawatt complex nearly 3 times more powerful than the Three Gorges Dam. The project is expected to cost about $167 billion. Construction began in July 2025, with completion targeted for 2033. Yet its extraordinary size is only part of the story. The dams are being developed in one of the most remote, mountainous and earthquake-prone regions on the planet. Before heavy machinery can reach the canyon, China must build an entire transportation network. The Pai-Gen-Medog Highway serves as the project's main supply route, carrying cement, steel and equipment toward the construction sites. New roads must be blasted into steep canyon walls, while bridges connect areas separated by deep ravines. Helicopters deliver urgent equipment to places that roads have not reached, and a cable car system transports workers across the gorge in minutes. Electricity, worker camps and construction platforms must also be established before the main work can begin. Every stage depends on the one before it. First the road, then the power lines, followed by camps, machinery and permanent access routes. The next challenge is controlling the Yarlung Tsangpo itself. During the monsoon season, the river carries an immense volume of water. Engineers plan to blast diversion channels through the surrounding rock, giving the river a temporary route around each construction area. Cofferdams made from rockfill and sealed with clay will block the original channel, allowing sections of the riverbed to dry. Once the water has been redirected, workers can inspect and prepare the exposed foundation. Loose and fractured rock must be removed because the enormous dam walls require a stable base. Engineers drill foundation cores, document the condition of the granite and inject cement into underground fractures, forming a grout curtain that prevents water from passing beneath the structures. The project portrayed in the video includes 5 cascade stations operating across the river's steepest descent. It also imagines 4 enormous tunnels, each approximately 20 kilometers long, passing through the Himalayan mountain. Giant tunnel boring machines would cut through the granite using hundreds of tungsten carbide disc cutters. As each machine advances, crews would install precast concrete segments behind it. These interlocking sections form protective rings that prevent the tunnel from collapsing. Groundwater, unstable rock and intense pressure make the work dangerous. Where water enters through fractures, engineers must stop, inject high-pressure cement grout and wait for the rock to seal before continuing. Steel penstocks would later be installed inside the completed tunnels. These pipes are designed to carry water toward the turbines at tremendous speed. Seismic sensors placed throughout the system would watch for movement in the surrounding mountains, an essential precaution in this earthquake-prone region. At the 5 cascade sites, the dam walls would rise simultaneously. Concrete plants positioned near each location would produce roller-compacted concrete, which can be delivered by trucks, spread in thin layers and compressed by heavy rollers. Cooling pipes inside the walls would control heat produced as the concrete cures. Every layer would be tested for strength and density before construction continued. Spillway gates would provide emergency control during extreme floods and powerful Himalayan monsoons. After the main structures were sealed, the temporary cofferdams could be removed and the reservoirs gradually filled. Together, the 5 stations would capture the energy of the river's dramatic descent through the canyon. Water entering the intakes would travel through the penstocks and strike massive Francis turbines inside powerhouses at the bottom of each cascade. The video describes 60 generating units in total, with each turbine rated at 1,000 megawatts. Spiral casings would guide the water toward the turbine runners, while adjustable wicket gates controlled its speed and volume. The spinning turbines would drive generators positioned directly above them. After surrendering much of its energy, the water would pass through draft tubes and tailrace tunnels before returning to the river. Transformers would then raise the electricity to extremely high voltage for transmission over thousands of kilometers toward eastern China. But the Yarlung Tsangpo does not end in Tibet. It crosses into India as the Brahmaputra and later reaches Bangladesh as the Jamuna. Around 300 million people across the downstream region depend upon this river system. India and Bangladesh therefore worry about how upstream dams could influence seasonal flow, sediment, ecosystems and emergency water releases. China argues that hydropower uses the river's downward fall without consuming the water. However, controlling the timing of storage and release still gives the upstream operator significant influence. The river crosses 3 countries, yet no comprehensive treaty governs the entire shared system. The Medog project promises an extraordinary supply of low-carbon electricity, potentially powering hundreds of millions of homes without burning coal. At the same time, it introduces engineering, environmental and geopolitical risks on an equally enormous scale. If the plan succeeds, the mountains will remain and the river will continue downstream. but the Yarlung Tsangpo and the nations depending upon it may never be the same again.